Good morning, everybody. I would like to discuss about you. And I would like to present to you some results we recently obtained in Poitiers. And as you can see, I will talk about some catalysts we prepare in our group, because we decided not to buy a catalyst and to control all the preparation until the application. And I will not give you some conclusion, but a kind of application, for example, we collaborate with a professor, Evgeny Katz, in New York, to activate with our catalyst a pacemaker. For example, you know that now we have a battery, lithium battery in the pacemaker, and to supply the pacemaker. And we can, for example, have some catalysts from gold, palladium, and platinum to protect them in the blood. For example, when you have around 10 millimolar of glucose in your blood, you are healthy. More than this, you have a diabetes, for example. So I have some slide about Poitiers. Poitiers is a nice place in the world, in France, because it's like you can discuss about Professor Ernesto or Germano. It's like San Carlos. It's a small city, okay? And if you wanted to taste good wine, you can go from Paris. There's a highway to go to Bordeaux. And you can stop a little bit in Poitiers, because it's the middle between Paris and Bordeaux, okay? And 1 day, 2 days, to visit, for example, our hall, it's a nice picture in the night. And you have a park of image. It's not a Disneyland, but it's like that. And you have, for example, our cathedral is that's in Portuguese, for example. Notre Dame is in the night. You have some pictures like that. It's very nice. Okay, and you're welcome in Poitiers. And if we have some at the university, it's a old university. It's the seventh in France. It's founded in 1431 by Queen Charles VII. And we have now around 23,000 students. And our laboratory, for example, belongs to these 42 laboratories in Poitiers. And now we regroup all the chemists in Poitiers in the big laboratory and institute. His name is IQSC. It's a big laboratory in France, because we have around 300 persons in the laboratory. In our group, we have around 30 permanent people. We have here 6 technicians, and the remaining persons are PhD and PDF postdoctoral trainees, for example. The group is SAMCAT, CAT as catalyst. And for what concerns our group, this slide can summarize all the activities we have with a lot of facilities. You have here, for example, with a solid polymer electrolyte fuel cell and a water electrolyzer. If we consider this scheme, we have, for example, here, the possibility to prepare. We have here, for example, a hydrogen evolution reaction. And if we wanted to construct, for example, a fuel cell, we need the HOR. This means hydrogen oxidation reaction against the reduction of oxygen. As you can see here, for example, when you have a fuel cell and you increase the current density, you have around the electromotive force around 0.65 volts. This is a good fuel cell. And by the way, if you wanted to construct electrolysis to feed, to supply your system, you have a problem because you need the splitting water to oxygen, and at the same time to reduce water to hydrogen. And this means that you need a voltage 3 times more than your fuel cell can deliver. This is a problem. Since 19th centuries. And we wanted to oblige this system to be reversible. This is a good challenge for electrochemists. At the same time, we have some solution. We can replace, for example, hydrogen by alcohol. Methanol is more toxic. Ethanol is good with cachaça. And we can take some alcohol like glucose, glycerol, for example. For biodiesel, for example, for South America, is a good fuel, glycerol. So I would like to give you some discussion about glycerol and glucose. And sometimes there's no Fabio, excuse. We are working about carbon dioxide reaction, for example, to reduce in formic acid on the methane and methanol. The best one is formic acid. As I told you, we prepare all the catalysts in our lab. This is, for example, some catalysts we prepare to be sure that we have here non-supported catalyst to study, to investigate all the catalysts without the support. Okay? And after, if we understand how this catalyst can work very well, we can add, for example, some conducting support like Vulcan carbon, casual black carbon, or something else. Carbon nanofiber, for example. And if you see here, for example, this is a resonance plasmon system with a UV to see cubic particles, for example, and it change with the color. If you have, for example, dark black band, you have some catalyst, like, for example, here, this is a kind of catalyst we can prepare with 111 index Miller facets. And if we wanted to discuss about this kind of catalyst, for example, I give you here term image, the distribution we calculate, and HR term. If you see very well, is the cubic one. We have a histogram to have the distribution size, for example. we say that we have around more than 80% of nanocube with is heterogeneous because it's not 100%. And if you have polycrystalline, for example, polyhedron catalyst, mainly you have 111 facet, and icosahedron and so on, for example. This means that we can, by the convolution, calculate, estimate the number of 111 facet, 100 facet, and 110 facet, for example, in the polycrystalline. We have some method in our lab. It's the same in Alicante with Feliu. We take here, for example, a wire of gold, and to reveal the orientation of the facet, for example. This means this is the method of UPD, under potential deposition of lead ad atom. By this method, you prepare, for example, this solution, and you apply a potential at 0.8. It's very important, because if you start here, you absorb all the species at the surface, and you have to restart, okay? You prepare your working electrode, you immerse in the solution at 0.8, and at the same time, you make your cycle, and you can reveal by this method the polycrystalline surface. You have 110. 100 is smaller, and 111, for example, which combine in this, you have polycrystalline catalyst, for example. So if it's work very well, we apply with the last catalyst I show you, and this means ABC. We prepare directly here, for example, in this catalyst, we have a surfactant, and we prepare the seed mediated, and after we add, for example, ascorbic acid as a reducing agent. At the same time, we change the reducing agent by sodium borohydride. It's with kinetics of the growth of the catalyst is very high. So we prepare this, and we have smaller particles with NaBH4. And the C catalyst is we combine one step seed-mediated surfactant, and we add borohydride, and we cool everything around 0 degree. And directly you have something, and the color change very fast. So we say that if the color change, we explain that the surfactant is ammonium bromide, and the metal precursor is chloride of gold. This means that at the beginning you have an exchange between bromide and chloride. This means that we can take this method to improve it, and after I will give you the new approach we have with this in our lab. We call it bromine anion exchange, because we can prepare now catalyst without a surfactant. Because when you have a surfactant, somebody can know, for example, the system of water enol mercury emission, for example. It's a good investigation in electrochemistry and electrocatalysis. When you have this method, it's very nice, so you have a good catalyst and manufacturing. But when you start electrochemistry characterization, you have problem, because you have to cycle 20 times to remove the surfactant at the surface of your active site. This means that if you can prepare something without a surfactant, it's beneficial for electrochemistry. But the problem is when you discuss with physicists, for example, they say that chemists are a good method to prepare catalysts, nanocatalysts. But the problem is organic compound. So we have a new method to remove the surfactant. We call it a surfactant-less method without a surfactant, and we improve the catalyst surface area.
Excuse me, can I ask one question? Yeah. You mentioned that for bone nanorods you have used seed-mediated growth method. Yeah. I just want to know about the nanocubes. Which method you have used for the synthesis of your word nanocubes?
To have a nanocube, you take CTRB as a surfactant.
In the same way, just like nanodes, for example, seed formation, and after that, by adding any...
You take, for example, for 1 minute, 30 minutes at the time, for example, because it depends on the seed size you have. And after you take this, you start your the growth particles. It depends on the size of your seed. And with a CTRB, you have some cube. And if you take, for example, how can I say, NaBH for borohydrate, sodium borohydrate, you increase the kinetic of growing catalyst. And in this, you can add, for example, if you want to have the nanorod, you add silver nitrate, for example. And at the same time, you have the growing in the one direction. You cannot have a cubic, you cannot have sphere particle, for example.
Okay, at which temperature you did your synthesis, for example, for nanocubes, let's say room temperature?
Room temperature. Better we control the temperature.
Okay, there is another thing I want to ask. For example, in case of nanocube, let's suppose we are using one surfactant, for example, a CTAB. Because we know that CTAB absorbs mostly on 110 passage. Yeah, on that passage. But let's say, for example, if we replace this CTAB with any other surfactant, for example, let's say a CTAC, having chloride ions, or by adding these two surfactants at a time, maybe it absorbs on one facet CTAB and other facet CTAC. In this way, we can get the nanocube.
If we wanted to have a nanocube, we take only a CTAB. CTAB as a surfactant. If we wanted to have a sphere, nanoparticles, we call it an ether bridge 30. It's better because you modified the mediating time, for example, and you can go towards a sphere, nanoparticles, and the CTAB is better because it's not a molecule, it's a salt, ammonium bromide. And you can play very well with the ammonium to have cubic nanoparticles. Okay? And after we can discuss about it. Let me continue, and after we will have a talk. Okay. And for example, if we can discuss about some particles, for example, I take the first, when we have all the particles at the same reactor. We deconvolute here, for example, the charge, the Coulombic charge of each peak, and we can say that after centrifugation, for example, you have this part of the charge of 111, for example, is higher than 110. And after chemical cleaning, as I told you, if you have some surfactant at the surface, you want to remove them, you can cycle your, during 20 times, for example, it's efficient to to remove some organic compound, and you change the distribution of the charge. And when you use lead oxide, it's a good way. You have to apply a potential at 1.2, and lead oxide can oxidize all the organic compound at the surface of your catalyst. And after you remove everything, it's a good way to clean the surface of the catalyst for investigation, for example, in TEM and so on. And if I return now, for example, to give you two investigations, I combine here a system in our laboratory. It's an in situ spectroelectrochemical cell. We combine voltammetry and spectroscopy in situ. So Brucker, for example, is known that this cell was constructed in our lab, and now Brucker can provide you with this kind of cell. What is working? It's working with, during the voltammetry, when you cycle, you record at the same time your voltammogram and the spectra. For example, we have two techniques. Here, for example, I combine CO stripping and spectroscopy. So at 0.1, for example, you absorb CO at the surface of your catalyst, and when you reach the double layer, you stop and you record your voltammogram. For example, you have the oxidation of, we discussed about it, the oxidation of CO, and after you recover your surface, and you can continue after. And at the same time, we record, for example, by this technique, spares. This means that we scan the surface of the catalyst. At the same time, we record CO stripping. By the way, we have here, for example, during from here to here, we record and we have two kinds of CO at the surface. We have CO is well known is a linear CO adsorb. Okay, but sometimes you have bridge CO. This means that at the surface you have two bonds. Thermodynamically, it's convenient to say that CO linear, you have one bond, so it's, to remove is better, thermodynamically. But in electrocatalysis, you are not in thermodynamic. You are a catalyst, and we have electrochemistry, there is a potential applied. This means that we have kinetics. Electrochemistry is kinetics system. At the same time, we have CO bond is better in electrochemistry to remove very easily bridge CO than linear CO. So if you have catalyst, you have a bridge CO is better than linear CO at the surface, because to remove linear CO, you have to go at high potential to remove this kind of poison at the surface. The second technique we have is sniff tears. Sniff tears means that by a modulation of the potential at a frequency around 25 millihertz, you have two potentials, lower one and the higher one, and you scan during 128 interferogram to have information in this interval. At the same time, for example, with Germano and the Riberon group, Paolo and Giza, we obtained, for example, for ethanol oxidation reaction, some information about the evidence of CO linear and this with CMOS. So, last year, in 2014, we tried from Riberon, San Carlos, and Poitiers on glycerol oxidation over palladium catalyst modified by manganese, iron, nickel, and some result with tin. We published in RSA Advanced. This catalyst is in front of your building. We combine infrared, cyclic voltammetry, and analytic HPLC, and after ex situ system mass spectrometry. And here, for example, we have some reference to see to assign all the particles, what can I say, the molecules we have. And if you can see here, for example, by HPLC, we have some product. It depends on the co-catalyst at the surface of palladium. So I show you the system we have. It depends. We have two chromatographies. Isocratic one, Dionex, HPLC. At the same time, by the way, you use sulfuric acid as eluent. And automatically, you have some system to inject the solution. So you can go to have coffee, and you see, okay. And you have a column, HPX is very important. This column is expensive, but it's a good column, a nice column. And when you use isocratic system, we use two detectors, UV, followed by refractive index. But in the second step, I will discuss with you glucose oxidation. Glucose is a big molecule, 6 carbon. So we cannot use, it's not possible to use this system. It's not good, enough convenient. We have ionic chromatography. Ionic chromatography with eluent is Enawaga, okay? And at the same time, we have an ion column. With an ion column, 15A, as we have some anion, for some carboxylates, we use conductimetric detector, and after we have an electrochemical system, amperometric detector. It's good to have, for example, you can have a voltammogram, and where your system can be oxidized, you take this interval to have the set potential you can include in the system. The best way of this system is not, this is common, and it's to buy a fraction collector. It's very important. And Vanessa, some of you know her. She stayed during 1 year in our laboratory. And she managed very well the system to have, for glycerol, the time to recover each peak, each analytic chromatographic peak. It's very nice. And after, you can collect all the fraction you have. And after, this is a chemistry. You remove the electrolytes by a resin, amberlite, DOX, and so on. And after, you can lyophilize, because glucose is very fragile. So you have to take something. You cannot take an evaporation system, for example. An evaporator is not good because it's very strong. in pressure, and you lyophilize your solution without electrolyte, and after you can make, if you want, mass spectroscopy. And now we try to combine with NMR. The problem is you have traces of water, and you have some ppm of water inside your spectrum in NMR. So we wanted to improve. And with this system, by mass spectroscopy, we have, for example, for the first time, the mass of the main reaction product, glycerate and oxalate. So by this way, we say we can improve the system. This means that we prepare, as I told you, by bromine exchange with chloride. We say that we have a student, Yaovi. He said, I can improve this system. So this is his apparatus it's a reflex system. It's very simple. And he had an excellent of a Cabier, bromide potassium. And at this time, he exchanged chloride of a metal precursor with a complex. So when he has this exchange, he heat at room temperature. It's not high. And after he can, if he wanted to add, for example, a connecting support like Vulcan carbon, for example, he can add. And after he dry at 40 degrees over the night, and he cover his metal. He works with 20 and 30% of metal loading. At the beginning, the system is not optimized. He has an XRD characterization, for example, with silver and nickel to modify the palladium. And we have a shift here. The system is, we can have an amorphous silver chloride in the system. So we can see very well this system. At the same time, we have here with XRD, the lattice parameter, for example, when you have nickel is lower than the parameter, lattice parameter of palladium. So we observe that we maintain the same lattice parameter. This means that when we include in the crystallographic structure of palladium nickel, it's very lower than the atom of palladium. You cannot change the lattice parameter. Conversely, when you have, for example, silver is larger than palladium, we see that we have something which is when we increase the content of the silver content, we increase the lattice parameter. And this is a theory. And the experimental values are higher than the theory. We explained that there is a problem during the synthesis. This means that when you use sodium borohydride, this precursor can give you, you have bubble of hydrogen. This means that the first nanoparticle of palladium catalyze the decomposition of borohydride. And at the same time, if you know very well, palladium is different than platinum. You have a network, and the hydrogen atoms can be included to as hydride in the crystallographic of palladium. And at the same, you increase, you have a dilatation of your catalyst. This means that we, at the place of 3.9, we have a 3.93 as an angstrom as a lattice parameter of this kind of system. We observe this, and after we can remove at around 100, because we have a system in a direct in situ, to increase the temperature and to remove all the hydrogen from the network. And after we decrease at 3.990 angstrom, the lattice parameter of palladium. And we have donc consequently an effect of the reducing agent. If we have sodium borohydride, can we change to avoid the insertion of hydrogen? We use, for the first time, ascorbic acid. This is a good reducing agent, and there is no hydrogen. The problem is the kinetics is very low. So when you take ascorbic acid, you have some larger nanoparticles, and we take it after because the surface is very clean, and we have no surfactant at the same time. So after, my conclusion concerning it. But when you use borohydride, you have smaller nanoparticles, very nice. For catalyst, it's the best one, because you have some defect at the surface. Is good for electrocatalysis. And we have a nanoparticle around 9, the mean particle size, 9 nanometers is the best one. And we consider that when you buy, for example, for Cabot Corporation, Vulcan carbon, you use as receive, you can have some problem of sulfur, because the manufacturing of this Vulcan carbon contains traces of sulfur. So we advise you to treat by heat treatment at 400 degrees with the flow rate of nitrogen, for example. During 4 hours, you can treat to have good conducting support. For example, this PhD student compare treated and untreated two kind of carbon, Vulcan, and casual black with high surface area, specific surface area. And when he treat on the without treating, for example, he can consider that here we have a higher surface area after treating his supporting. It's the same catalyst deposit at the surface treated and not treated. The difference is very high. And after he combined two techniques, electrochemistry for characterization, for example, his catalyst, and he compared with water in oil microemission method with his method. The difference is the surface area. Here he multiplied by 2.5 the surface area when he used a method without surfactant. This means that when you finish with water in oil, you have some surfactant molecules at the surface which absorb at the surface of your catalyst. Okay. And he prepared, for example, CO stripping, and we consider that this is very known. With palladium, you have your system with a CO stripping, CO oxidation. And when you use a co-catalyst, you shift the oxidation of CO at lower potential. And the problem is, how can we oxidize CO without oxygenated species at the surface? This is a big problem in a catalyst. Here, we can say that we have a bifunctional Langmuir-Hinchelwood system, because at the surface you have OH, which cover your platinum, palladium catalyst, so you can remove by Langmuir-Hinchelwood mechanism. For example, you combine and you have CO2, and after you diffuse in the solution to become carbonates in an alkaline medium. But when at 0.4, there's no oxygen, there's no oxygenated species at the surface. But we have a reaction. That means here. So Vicoxy is the first author with a Spinel law to propose Euler-Udil in electrochemistry, because in catalyst it's well known that Euler-Udil can be exist. But we have no evidence. We publish here and we say that it's Euler-Udil. And the referee say, oh, have you evidence? You have no evidence. So remove this paragraph in your manuscript. So as we wanted to have our paper, so we remove. But it's needed to have some evidence to say that Euler-Udil can be exist. Maybe with nanobalance combined with some techniques. This is. But when we combine with spares, for example, we have some idea. As you can see here, at 0.4, we have oxidation of CO to CO2. We have some evidence, but it's not enough. This means that at 0.4, but we have to prove that we have oxygen at the surface. We cannot have this evidence. And with co-catalyst, with nickel, we have at the same time very earlier CO oxidation to CO2. This means that we can propose something with combining HPLC, spectroelectrochemistry, and mass spectrometry to propose this mechanism, for example, a scheme, where each product was given as evidence to propose this, and we have CO adsorbed as linear species at the surface and so on. So this is with the combination of different technique. With glucose, we would like to change carbon, graphic carbon, because hybridization sp2, sp3, for example, with graphitic, is not interesting when you apply a high potential. For example, you can oxidize, for example, graphitic carbon to CO2. So we use carbon nanofiber. And as you can see, we increase the current density by changing only the supporting conductor. This is very, very, very high. And during 4 hours, we carry out electrolysis, for example, at the surface of this catalyst. And we can see the decreasing for the current. We remove, as we did it with glycerol, and the remain product after lyophilization, neutralization, and after we recovering to mass spectrometry, we have in chromatographic analysis this gluconate by comparison with the reference. And after we recover the solid product we have after lyophilization to inject in mass spectrometry, we call it negative ionization of the system. We have here, for example, the mass of gluconic minus proton, 1. So we have here the mass of gluconic acid in the mode negative ionization of the product. This means that when we know very well glucose because I did my thesis with this molecule. And here, for example, you have an isomer here, alpha and beta. Here you have OH here. And this means that the more reactive compound among the two isomers is beta-D-glucose. This means you have here the first removal of this hydrogen. We call it dehydrogenation of glucose. And after that, you have a lactone. This lactone can be diffused in the solution to become gluconic acid. As conclusion, there is no conclusion, we have here, for example, an application. The application is to activate a pacemaker with our catalyst and so on. This means that this technique is without membrane to separate the cathode and the anode. Okay? And there is another system with we activate the student send the result to the supervisor in New York by wireless after his system in orange. So very nice. Yes. And the first one is two applications. The first one is with pacemaker activation. He takes his nanocatalyst without enzyme. There is no enzyme. And he prepares, when you have this concentration of glucose, this means that you are in a rest position. Okay? If you move, you consume your glucose. And after, if you have a diabetes, the concentration is more than, it's like that, for example, 10 or 20 millimolar glucose in your body. So this means that, as you can see, when you use glucose, you have an OCV, or open circuit voltage, very good, convenient for this application because you don't need 1 volt, you don't need 1 amp, because if you have in your heart 1 amp, you can the patient can be die, you know, and you want to save him. So it's very convenient. And after you have electronic system to increase inside here, for example, you can put this electronic device to amplify the voltage. This is enough. And after, the device works during 12 hours without problem. And this kind of application from the catalyst until the application we wanted to propose as we work in our laboratory. This, I'm here with my colleague Karin because of collaborative program, CAPES Cofecube. You know, you say CAPS, not CAPES. CAPS Cofecube. And I would like to acknowledge the students and my colleagues, and particularly my colleague here, Assistant Professor Dr. Karin, and the group of San Carlos, because I stay here for the first time in 1998. And each year, I don't improve my Portuguese. Because when I return, I forgot everything. And all the students, when they arrive in Poitiers, they wanted to improve their French. So you have to speak in French. Okay, Marcia? Okay? And so I would like to thank you for your kind attention, and if you have some question, I can discuss with you. Thanks.
I have one question regarding the hydrocarbon part of the application. Up to what extent that hydrocarbon part is important in the formation of nanoparticles? For example, if we reduce the number of carbons in the hydrocarbon, it will have the same effect, or the effect will change with this carbon by changing this carbon.
The supporting carbon, or the compound in the from the capping agent. Yeah. It depends. If you use, for example, tannic acid, you decrease your tannic acid because it's 60 carbon inside. You can decrease very well the nanoparticle size, okay? But the problem is it's very acidic, and you change the morphology of your catalyst towards a nanosphere. But when you use ammonium bromide, CTAB, and you can use, for example, some polyvinyl, for example, PVD, you can have, it's a organic, more organic system. So you can change the morphology of the system. But you cannot, the inconvenience is, the disadvantage is the particle size. It's more homogeneous, but after you have to recover your catalyst for electrochemistry. It's very, very difficult to remove the solvent, organic solvent. This is a problem of organic capping agent and so on. But when you have sometimes, for example, water as a solvent, and you have a molecule that bridge, for example, is a nice system in the micro-emission water enol. We prefer bridge is an ether. And after you can remove very easily your bridge, even if we have evidence that some bridge molecules remain at the surface of your catalyst. Because if you have some papers from Abreu in electrocatalysis, I think, we propose how to clean 2 times with acetone, with water, and after with ethanol, to remove more the bridge at the surface of your catalyst. Because it's an ether, and it's easier to remove than CTAB, PVD, and so on. So, this is my explanation.
There's another thing in the bromide exchange method that you have used. You have tried with bromide, and have you tried with other halogens as well, let's say with chloride and any other halogens, or not just with bromide?
We use a chloride metal precursor. And the idea is because in industry, they use iodide. And it's larger, bigger than, and we intend to propose something like that. Yeah, but we don't start. If you want, you can start, and you call me, okay?
there's another thing when you have mentioned under the position of that. I could not get your point clearly. Like you want to say that we have to start higher potential, for example, 0.8, and then we have to go to lower.
You know UPD?
Yeah, I tried once, but I could not get that.
You have, UPD is, if you start at lower potential, you have a metallic bond, okay? So if you have, for example, minus 0.13 volt, sorry. If you, to have an atom, you have to start higher, at potential higher than the metal, the redox value, okay? This is UPD. In this case of, if you want to reveal the orientation of your surface, you have to start the potential applied at higher potential. Why? Because if you start here, you have UPD at the surface directly. And so you absorb. Yes, exactly. This is why if you start at a higher potential, at 0.8, you absorb. It's like normally when you wanted to record a voltammogram. Usually, a lot of students start at 0.05. No, it's not good. You know why?
Because of these depositions?
No, because the standby of your potential star give you some value, maybe at 0.5. So you have to look at this value. And with your potential star, you can take free potential. The standby potential to be that backup, because if you start at lower potential, you force your potential star to start at 0.05. So if you take this value, you record, and after you start at 0.05, and you continue. This is more convenient for your system. This is why, in the case of, if you want to reveal something like that, you can use gallium and copper. It's proposed in the literature. You can see according to the catalyst you have. By the way, for us with gold, palladium and platinum, we use lead atom. It's better because the size of the atom of lead is convenient for this kind of catalyst.
I tried a lot of time by using this UPD, but I could not get that. Then I was thinking there is something wrong with lead nitrate. So I changed all the time lead nitrate. Every time I tried to change.
I say to the students that if you wanted to prepare something like that, you have to work very properly, any traces of impurities at 1 meter around you. Okay? But yes, it's very sensitive as techniques. So if you have something at the surface, you have not the same peak, and you can change a lot of things at the, but normally it works. No problem.
Instead of morphology of the particle, like platinum morphology, for example, do you have some characterization that indicates a homogeneous distribution of the palladium or nickel, or some segregation, or?
No, it's not. This preparation, we have techniques with, we change with polyol method to have caution. This is not this system. This is to have the modification of the system with the co-catalyst. The problem you have, if you work with a nickel, for example, you have no contrast to see very well the difference between palladium and nickel. This is very difficult. But when we, by XRD, we have no, we have no evidence of the presence of nickel. In HRTM, we have some, because we can make ADX in the environment to see we have what kind of, the percentage of nickel. This is our solution. But with XRD, we have no evidence of nickel. Yes.